Hello, hi everyone. Today I'm going to present our work entitled ECN Works Better for Selective Dropping in High Bandwidth Delay Product. I am the first author. My name is Mahmoud Bahanasi, and this is a cooperation work between Huawei Canada and University of Toronto. To give you a background about the problems that we are trying to solve, modern internet services and applications distribute data and compute in different geographical distributed locations. One famous example for this is terrestrial observatories or remote telescope that they collect huge amount of data and then they transfer those to another location for processing. To handle congestion in such systems, existing solution leverage either ECN like DCTCP or DCQCN, or maybe delay like Vegas or Timely. Some other congestion control might also use packet loss. However, using any of these methods does not guarantee zero packet loss. There is a few reasons behind this. One of them is traditional TCP reaction is very slow, and this is basically because it has to wait for 3 duplicate acts or wait for RTO to expire in order to trigger retransmission. And therefore, we need a faster way to trigger packet loss recovery. Another reason is when congestion happens inside DCN, it takes thousands of times compared to the DCN RTTs from the DCI to react to this packet loss. Basically, if you have a data center network, you could have 5 or 10 microseconds for the RTT inside the data center. However, you could have 3 or maybe 10 milliseconds for the RTT between two data centers. And this makes the behavior of the DCI traffic affect heavily the behavior of the DCN traffic. For this, we identified 3 main congestion points in such system. First congestion point is inside the source data center, which we marked here as 1, and in between the 2 data centers, which we marked here as 2, and the third one is inside the destination data centers. We are more interested in points 2 and 3 between data centers and at the destination data centers in this work. For this, we need to identify few characteristics for such a system. For example, we have very high latency, hundreds of milliseconds, and therefore the reaction mechanism is very slow. And we have heterogeneous traffic. DCI and DCN traffic are living together in one big system, and we do not have any explicit feedback from the intermediate routers between the 2 data centers. So any routers in between could lose a packet without notifying the source about this packet loss or anything. So we can also achieve some guarantees from the SLA or can use statistical multiplexing to enhance our performance. For this, we considered a few points for our design. The main idea for us is to introduce a new reaction to packet loss in the WAN without triggering the host reaction. So for this, packet loss recovery takes place at the edge routers, and it recovers packet faster while preventing TCP conservative behavior. Our solution is designed as a pluggable to existing TCP, so we are not replacing existing TCP mechanism, we are adding our solution for existing TCP protocols. In case of severe congestion, we need to make sure that we fall back to the baseline, which is the TCP that we are using in our system, and we do not need to degrade the system more than that. And we need to provide a faster recovery for packet loss for DCN and DCI connection. So for this, we have considered this design. The source routers would send traffic, or the source data center is sending traffic to a destination data center. While sending traffic, the source router will mark certain number of packets, and this mark we call them ECN disabled, meaning that these packets will be disabled from the ECN flag like 00, and other traffic, the normal traffic, will be enabled from the ECN point of view. So any routers in between, when it sees this flag, the packet that is enabled for ECN, he will mark the packet and keep transmitting, but those packets that are not marked, they will drop the packet. And those packets that we are marking for drop, we basically are going to copy or keep a copy of them at our source routers here, and when this marked packet reaches router B will generate an ACK between the two routers. Here, for example, we have lost packet 1 and 2, and router B was able to generate an ACK for packet 3, and therefore we can basically send a retransmit packet 1 and retransmit packet 2, and when we see the ACK for packet 3, we drop packet 3 and we move the head to the next available packet in our system. We also considered adding integration using BFC and ECN, but we left this for future work. So for this, we needed to design two main queue disciplines. We call them Q1 and Q2. First, Q1 is the source or the transmitter queue here, which takes care of marking the packet with a certain percentage and copying certain packets to the low priority queue or a stalled queue in case of we have enough memory. And then route QA, which takes care of generating the ACK for the received packet towards the source router. Those two disciplines are the algorithms for two queue disciplines are presented here. For more details, please refer to the paper. One interesting comparison is some internet providers prefer to end or terminate the TCP traffic at the edge routers and establish another TCP connection between the two edge routers, and then establish a third TCP connection between the second edge router and the host. This would definitely enhance the performance because we can see that the loop for the TCP connection is shorter. However, this edge routers needs not only to store all in-flight packets, but also need to keep the state of each connection both to the host and to the other edge routers. So we need to keep a state for the connection between the host and the router A, and also we need to keep a state for the connection between router A and router B, which also include the data packets in this connection, not only a state by some counters or for the TCP. We also need to keep the data itself in our system for retransmission between, for example, router A and router B in case of packet loss. Which means that our system would have a very low overhead in terms of state at the router or data keeping at the routers. For evaluation, we conducted several experiments. First experiment, we simulated two data centers. Each data center has 15 hosts, and we generate 15 long-lasting flows from data center A towards data center B, and we ran this experiment twice. One while we assuming that there is a cooperative LAN, and we enforce the packet drop to happen only for the ECN disabled packet, and we artificially drop 5% of the traffic. And we also repeat the same experiment while we assume that the DCI link is non-cooperative, or the WAN is non-cooperative, meaning that the packet loss happen in all packets regardless if the packet is marked or not marked. We can see that for the first case, when the WAN is cooperative, we can achieve up to 6 and 4.5% improvement for TCP Reno and TCP cubic, and for non-cooperative WAN we can achieve 4x and 3.24x for TCP Reno and TCP cubic. For more details about the results and please refer to the paper. We have also conducted another experiment to validate the performance with different RTT values. So in this experiment, we changed the RTT value to represent longer distance in the system. We start with 10 millisecond up to 30 millisecond, and we can see the performance we can achieve up to 5x or 7x in terms of the performance compared to TCP, the base TCP cubic or TCP PBR. We also noticed that DCIP gain increases as RTT increases, as we can see, because as RTT increases, TCP will perform very bad because the long control loop affects the performance of the TCP itself. We also conducted a third experiment for a realistic workload. We have used web search workload and we generated 1000 flows, and we tried to maintain the load in the network up to 80%. And we use base TCP, in this case was TCP cubic, and the figure illustrates that we were able to achieve 88% improvement in the flow completion time. To conclude our work, we presented DCIP as a pluggable for TCP to enhance the performance of inter-data center communication. DCIP uses the ECN marking to selective drop certain packets instead of sending congestion, as ECN is usually used for. And it also allows intermediate routers to drop recommended packets that can easily be recovered, and therefore we can avoid causing any TCP sphere reaction at the host. Our experiment shows that DCIP can increase the performance by 6, 4, or 7x compared to TCP Reno, Cubic, and BBR. As a future work, we're considering defining an interaction between DCIP and TCP at the host, which should allow us to increase the performance. This is all our work regarding the presentation. Thank you, and happy to have any questions. Thanks.